This video will cover the synthesis of epoxides through a base-promoted cyclization of halohydrins. The mechanism of this reaction is just like that of the Williamson ether synthesis. The difference is that the nucleophile and the electrophile are both in the same molecule, a molecule of halohydrin. Remember that we talked about the synthesis of halohydrins last semester. In this reaction, we need a strong base to deprotonate the alcohol. Typically, sodium hydroxide is used. The base deprotonates the alcohol to make it a better nucleophile. In the next step, the nucleophile attacks the electrophile in an SN2 reaction. This produces the epoxide. This SN2 step is an intermolecular reaction. Typically, intermolecular reactions occur very quickly because the nucleophile and the electrophile are already very close together since they're in the same molecule. The fact that the last step of this mechanism is an SN2 reaction requires that the nucleophile and the leaving group are trans to one another. Let's look at an example. If we treat this halohydrin with a strong base like sodium hydroxide, the alcohol will deprotonate, producing the alkoxide ion. If we redraw the alkoxide ion to be looking down the ring of the cyclohexane, we can see that the nucleophile and the leaving group are positioned correctly for an SN2 reaction. The nucleophile is able to attack from the back, kicking off the leaving group to form the epoxide. This reaction will not occur if the hydroxyl group and the leaving group are cis to one another. Fortunately, if we think back to the synthesis of halohydrins, we will remember that this synthesis is stereoselective and only ever produces the anti-addition of bromine or halogens and the hydroxyl group. Let's look at an example. Halohydrins are synthesized from alkenes. The reaction occurs when an alkene is treated with a halogen and water. Remember that the mechanism proceeds through the bromonium ion. This produces two stereospecific products. The synthesis of halohydrins is both stereoselective and regioselective. It's regioselective in that we see Markovnikov addition of water. Notice in both cases that the hydroxyl group adds to the carbon of the alkene that is more substituted. We also see that the synthesis of halohydrins is stereoselective. The bromine and the hydroxyl group add anti to one another. Remember that this mechanism goes through the halonium ion. This is what results in the regioselectivity and stereoselectivity of the mechanism. Take a moment to pause the video and make sure that you can draw out the mechanism that predicts both of these specific stereoisomers of the products. The mechanism for the synthesis of halohydrins should look like this. Remember that the attack of water on the bromonium ion is an SN2 reaction, requiring the water to come from the opposite side that the leaving group will leave from. This gives us the trans stereoselectivity. Finally, it is important to note that we can use the base-promoted cyclization of halohydrins to synthesize other, larger cyclic ethers than the epoxide. For example, we can synthesize a four-membered ring ether using this halohydrin. If we treat this halohydrin with sodium hydroxide, the alcohol will deprotonate and cyclize to form the four-membered ring ether. However, because the nucleophile and the electrophile are not as close together as they were in the previous examples, the intramolecular SN2 reaction is slower. This is the reaction that results in the cyclic ether. Because the intramolecular reaction is slower, the intermolecular SN2 reaction, with hydroxide acting as the nucleophile, can compete, and we get a significant amount of this product as well. Again, the reason that we get a significant amount of the intermolecular SN2 product, the diol, is because the nucleophile and the electrophile are further apart, making the intramolecular reaction slower. In order to prevent the intermolecular SN2 reaction from competing with the desired cyclic ether formation, we need to use a strong non-nucleophilic base for rings larger than the epoxide. A common strong non-nucleophilic base that is used is 2,6-lutadine. This base is too bulky to be nucleophilic, but it is a very good base, and it can promote the cyclization of larger cyclic ethers than epoxides. If we treat the halohydrin above with 2,6-lutadine, we see mainly the ether product, with no competing intermolecular reaction.